In this video, I'm going to show a demo of a game engine using GL and C++. GL and X11 need to be installed to get this working, along with a compiler like G++ for Linux. The engine's not yet working for Windows, but that's to be done, and I'll re-upload the video as the project gets updated. I'll be using Blender to export scene geometry to C++ function. And in this implementation, I've got a few features working, and those are basically to draw triangles and color them, or to load an image from a file and draw it to the face of the triangle. In this version, textures have to be loaded first, so they can't be attached to objects that move, because moving objects are loaded last, and that's one of the first things I'm going to fix. Another problem is that an object with a texture has to be split into parts. So for this cube, there's an object for each of the 6 faces. The spheres have a simple custom shader that uses the object's vertex normals to set the brightness of the object's color. And I'm going to show how to make a skybox, which is basically a cube that surrounds the camera and has an image attached to each direction. And in this program, a function is made for the translation, scale, and rotation of objects, as well as any children that were parented to the object in Blender. And obviously there are functions for reading input and moving the camera. And there are still a few basic things missing, like sound and drawing of transparent objects. And the code that I'm going to show will have some bugs, but hopefully most of them will get cleared out in time. Other features that anyone would want to implement has to be done by writing C++ code, and that can be quite a bit different from creating a game in an IDE, but I'm interested in doing it this way because the code can be repurposed for different applications. So here are the project files. There's a main.cpp file that has the main game code, and a main.py file exports the game scene. The make file builds the program. And in the code folder, there's more C++ code. The scene folder is for blend files. And the script folder has more functions for exporting geometry from blend files. Before the game is run, an export script needs to write geometry and game settings to a file. So first I'll show how to use this script to get the engine working, and then I'll go back and show the code for the project. So at the top of the script is a list of Blender scenes to import. There's one for objects that don't move and one for objects that move. And the first list would be things like terrain and buildings, and the second list is for scenes containing characters and any objects that, say, a character might pick up. And in this implementation, there's not a lot of need to do this if you weren't using textures. You could just add everything to the dynamic object list, and dynamic objects will be able to use textures soon, but in the long term, the purpose of separating static and dynamic objects is for efficiency. So for now, I'm not going to add anything to those lists. I'm just going to run the script by typing python.3 main.py into the terminal. And that's created an object folder, and in that folder is a data folder, and that has game settings that get passed back to main. So now if I want to build and run the main program, I first need to set my build commands. These are those linker flags that are also in the makefile. Then I can build and run my program, and I just get an empty scene. So next I want to add my textured cube. So I'm going to copy in my scenes to my scene folder. That scene looks like this. It's just a cube in the center of the screen, but each face is its own object. So I'm going to add that scene to the top of the list. Scene texture.blend. And when I run my script, I'm going to get an error. And that's because I don't have any UV data in my object folder. So I need to export that UV data, and I need an object folder for each object. So there are 6 faces. And I'm not sure how to export UV data using Blender 2.7, so I'm going to use Blender 2.8. And attached to this screen, to this scene, is a script called uv.py. And for some reason, Blender, when it exports these, it's going to read these objects backwards. Maybe it's the reverse order of the objects that were created. So I know that this last object has an identification number of 0. So I'm going to run that first. And now in the object folder for 0, I have 4 vertices for that face. And for each of those vertices, I have a UV coordinate that corresponds to a position on the image. So I'm going to do that for the rest of the objects. This one is 1. Then I'm going to run my export script again. Now when I run my program, I'm going to get an error because it can't find the images for the face of the cube, and those go in the same folder. So I have those textures here. So I'm going to copy each of those into each object folder. And those all have the same name. It's all text.bmp. So now when I run the game, my scene is spinning around, and that's because camera rotation is caused by the difference between the pointer and the center of the screen. So what I want to do is enable the warp pointer option to lock the cursor in the center of the screen. I'll also go ahead and hide the cursor, even though you might be able to see it in the recording. I won't be able to see it on my screen. I'll go ahead and move the camera out of the center of the box. Then I'll compile or rebuild and run it again. Or I forgot to re-export. That will overwrite the old game settings. And so there's my textured cube. And this is basically made by rendering 6 images of noise texture in Blender. Now I'm going to import my new scene. It's just a bunch of scattered cubes. So to do that, just add it to the list. And a re-export and a recompile. I'll rebuild. There are my new objects. Now I'm going to import some dynamic objects from this scene. I've also got some parenting. So the child objects inherit the transforms of the parent objects. I've also added a material to each object that has a prefix of norm, and that's a flag for my export script to load a custom shader. So I'm going to add that scene to the dynamic object list. And now when I rebuild this, it's going to take a lot longer. That's because the spheres have a lot more geometry than the cubes do. So there are the spheres with the normal shader applied. And it's different from a light, because the light has a lot more sudden fall off. This has a very gradual fall off. But it definitely adds some depth to the object. If I were using a flat shader like I did on these cubes, they would just appear as a circle. So next I'm going to add a skybox, so I'm going to set sky to true, and I need to add a folder with some images to the object folder, and those are here, and they all have specific names. So I'm just going to copy that and drop it in there. Re-export and reload. And now I have my skybox, and the images that I'm using for this are a bit crude. They're also a work in progress, but I think it still adds a sense that the scene is much larger than it was before. Part of that is because the render was made from high up. Also, each image has a resolution of 4096 by 4096 for 4K. I tried 1024, but it was kind of fuzzy and made the scene look a lot smaller. And to create this, I rendered 6 images, each facing a different direction. And the camera had a square resolution and a viewing angle of 90 degrees. And a good skybox can make a big difference in how a scene looks, but it also needs to be balanced with the scene itself in different ways, like how sparse or dense the scene is. The last thing I'll show is how to get these objects to move. So first I'll add some new keys to the key held array. And in the input function, I'm going to use X11 to check if any of these keys have been pressed. R is going to rotate, T will translate, and Y will scale. Those are in the 6th, 7th, and 8th position of the key held list. The first block is for key presses, and the second block is for key releases. And then in the move function, I'm going to check if those booleans are set to true. This is 6, which corresponds to R. If R is being held, I'm going to call it the rotation transform function. And I need to pass the dynamic object list. and I'm going to move the 0th object in that list. I'm going to rotate it by 0 and X, 0 and Y, and 5 and Z. For the T key, I'm going to call it location translate, and I'll move that by 0.1 in Y. And I'll scale the object by 0.1 in all dimensions. So now the child objects can move in there, or the object can move and its children moves along with it. I messed up the scale, obviously. I meant for that to be 0.1 as well, but I think you get the picture. So that's it for the demo. Next I'm going to explain a few concepts that make the game engine work. And a lot of the program is just managing data, since GL handles most of the math. But there are a few things that need to be done manually, like moving the camera and moving child objects. And to get these concepts, you need to know the basics of vector math. So I'll start by explaining the camera. And my camera is basically made up of 3 orthogonal vectors, as well as another vector that represents its location. The camera has a vertical vector, and I'm naming that V. It has a horizontal vector, which I named U. It also has a depth vector, which I'm calling W. The camera object is defined in the object header, and here it is. Here's the location. Here are the 3 vectors that give the camera's orientation. There's a near and far for the camera clipping, and I'm not actually using this since my demo only has 1 camera. I'm actually passing those clipping points straight to GL. This is the near clip and the far clip. So when a new camera object is made, this constructor for the object is automatically called. And I set the U vector's first dimension to 1. And that corresponds to this point here. And it can be written like this: X, Y, and Z. The forward vector, the second dimension gets set to 1. That corresponds to this point here, and it gives a vector that looks like this. And lastly, the V vector, the Z is set to 1. And what you basically have here is an identity matrix, which I sort of think of as like a default matrix, because it has a total area of 1. Also, each axis is aligned with the world axis. So the first thing I want to do is to get my camera to be able to swivel left and right based on horizontal mouse movement. So horizontal mouse movement is detected using X11 in the input function. That's right here. Here's horizontal movement, here's vertical movement. These diff X and Y values get passed to move. And the first thing I'm doing here is creating an axis that points straight up. So let's say my camera is kind of pitched down like this. I have a vector that points straight up, and that's different from the camera's vertical vector since this is kind of pitched down. But this acts as a constant vector that all the vectors of the camera rotate around. And to perform that rotation, I use the quaternion function and just rotate one axis of the camera at a time. This is the angle that I want to rotate the camera by. This is the axis I made that points straight up in Z. So the next thing I want to do is add vertical mouse movement to the camera. And instead of a global vector that's going to rotate the camera around its own U vector, another thing I have to do is to stop the camera from rotating beyond vertical. If it does, the camera could end up upside down. Same as being beyond pointing straight down. If it passes that point, it could end up upside down. So if I keep pulling the mouse down past this point, I want to lock my camera into that vertical angle. So to do that, I'm checking the camera's V vector. If you notice, the camera will pass vertical as soon as that V vector crosses the horizon. So I can dot this vector with a world vector that points straight up, and if that dot product is less than 0, then it means my camera has passed vertical. But if it's greater than 0, then my camera has not passed that vertical point. So here's that dot product. It's the camera's V vector, which I've actually copied here, dotted with a world Z vector. The other thing I want to know is whether or not my camera is pointed above the horizon like this or below the horizon like this. And to do that, I can use the camera's forward vector, which points in this direction. And I'm also going to compare that to the world Z vector. And if it's less than 0, my camera is below the horizon. If it's greater than 0, my camera is above the horizon. And that's this dot product here. So if my camera is above the horizon and it passes vertical Z, then I'm going to set my camera to directly vertical. If my camera is below the horizon, I'm going to set my camera to face directly down. Multiplying by -1 just basically inverts this vector, so this is a world vector that points down in Z. If my camera does not pass that vertical threshold, then I just go ahead and set W and V to this vector, to these temporary vectors. And so that's how I set the orientation of the camera. This next part is for moving the location of the camera. So the first thing I want to do is get the angle that the camera is facing in XY. So to do that, I basically get a vector that points in the direction of the camera, and I read its X and Y location. And then I just use the arctan function to get the angle that the camera is facing in the XY plane. And the arctan function only works in the first quadrant here, but arctan2 will figure out what quadrant these points are in. So that's what I'm doing here, but there's another case where if the object is close to being vertical, then the X and Y values for the forward vector become very small, so the camera could start to move in random directions as it starts to approach and leave being vertical. So in those cases I'm going to use the V vector instead, because these X and Y values will be much more reliable when the camera is almost straight up or almost straight down. So that's what I'm doing here. I'm reusing this camera vertical dot product and taking the arctan of a different vector. So then when my W key is being held, I just move my camera in the direction of that angle. Sine corresponds to Y, cosine corresponds to X. This is the X key. It's basically the opposite of W, so I just have to subtract it instead of add. Here's the D key, which is right, so I basically just have to subtract pi over 2. And the A key is the opposite of D, so I just subtract instead of add. And then here's Q and here's E, and they just change the Z world location of the camera. So that's basically camera movement. The next thing I wanted to talk about is how child objects move relative to the parent. So for translation, it's pretty straightforward. I just move each child down the list the same as the parent. The rotation is a little bit different. For each child object, I have to draw a vector from the parent to the child. Then when I rotate the parent, I want to rotate that vector as well. Then I add this vector to the object's world location, and I'll get this vector, which represents the new world location of the child object. Then I draw a vector from the old location to the new location and update the child's location by this amount in this direction. And scale it works more or less the same, except I scale this vector instead of rotating it. So that's here. Child list gets all the object's children and all the children of those children. It also adds the object itself to the first element of the list. So I just have to iterate through this list and add the X, Y, and Z values for each object. In the rotate function, here's that vector I draw from the parent to the child. Then I rotate the vector, add the parent location back in, and then get a vector from that world location to the child's old location and move the child by that amount. And I start with the first child and just rotate the parent before I enter the child loop, and then I update the child's rotation as well. Scaling is pretty similar, except I'm getting a ratio of the old scale to the new scale, and then multiplying each dimension of the vector by each dimension of that ratio. So that's basically how that works. So now I'm going to show the code for the whole project, starting with this main file which exports geometry. The options that I haven't talked about are the program directories. There's this light which is used for the custom normal shader, and it basically points towards positive XZ or up into the east. Interval gives the number of elements before a data file is split into a new one, and that prevents any one data file from becoming too large. The write boolean is whether I want to write files to the hard disk. Game options, window resolution, camera speed, camera location, background color. Do I want to use a skybox? Do I want to use full screen? Do I want to lock the mouse pointer? Do I want to hide the cursor? Print statements to the console. And this value makes the game run at 60 frames per second. I first write general directories and files to the hard disk, and then I make a scene list for all scenes, static and dynamic, and I add an empty string as a flag that the static scene list has ended, and handle that there. This is the block that actually exports geometry data. So I have an export script that gets read and modified and then rewritten to this script. So the export script looks like this. It basically just writes object properties and data to a file. That's not the script that's used though. This is the script that's actually called. It has just basically these three variables added to the top. That's the only difference. And that's how I pass variables from main to a given scene in my scene list. So here's os.system. OS is a Python module, and system passes a command line string to the console. And here I'm basically telling Blender to run in batch mode and to run my scene and to run my temporary Python script. So if you want to see a list of command line commands for Blender, you just type --help, or if Blender is installed, you can just type Blender and then --help, and this shows a bunch of commands that can be used. And I use this a lot to do batch rendering of scenes. If you have a scene that has a lot of images to render, you can manage that using a Python script and a console command. And here's the script, or here's the command that I'm using on the given Python script file. So next I'm reading a written element counts like vertices and polygons. Then I process the child list. I basically convert it from names into indices. Here are skybox options. This is a skybox geometry. But I ended up actually not using these lists. I hard-coded them into my C++ program because that was just easier. So there's a little bit of work to do here. Here's another problem. All of the data lists that get passed to GL need to be parallel. So if, for example, an object has no color or an object has no UV data, you need to pad those lists with empty data so that the next object matches the correct index. But this is not done correctly. It still works, but it might cause problems in some situations. Here I write the object properties. In this section, I write the vertex list. Here's the normal list, then the color data, and the UV data. And then I write the data for that object to a file. Then here I create the main data C++ file that loads all these individual object data files. Here's the load function that gets called in the main program, but it's defined here in this data.c++ file. Here are game options. Here are the load declarations, and here's where they're called. And here is where the objects are initialized. The location for stationary objects is applied since they don't need to be run anymore. Loopend decides where to split a file into a new file to keep any one file from getting too large. Next is the game.py script. And here are more functions for exporting object data. Here's the object class, which has some object attributes. The write function writes those attributes to a file, and the read function reads them. ShaderGet checks whether to use flat shading, normal shading, or texturing, and returns a UV list if the object has one. DataGet uses Blender to get the object geometry. DataWrite writes geometry and other data to a file. DataRead reads it from the file. The ident file stores the count of objects that have been processed so far. CountRead reads the count of lists like vertex and polygon lists for all objects. And the reason that's needed is because in this implementation, GL is reading geometry from a list of all objects. So the vertex list is one big list for the whole scene. CountWrite updates the list. Object read passes the function parameters to the object. VertNorm calculates the color value for each vertex of an object based on the vertex normal. The UV.py script gets the UV data for each vertex of an object and writes the data to a file. So now the C++ code. Here's what that data.c++ file looks like. At the top of the main file are includes and function declarations. loads object data and properties. Initialize creates a window and sets up GL and X11, and that's defined in the window.c++ file. Texture initialize loads images for textures, and skyinit loads the skybox images and sets up GL. Both of these functions are defined in the image.c++ file. Time variables set up the game's frame rate. The xPending function is an X11 function that checks for events like user input. If input is detected, the key held list is updated, as well as these mouse cursor change variables and the running variable, which exits the game loop. If more than a 60th of a second passes, a new frame is processed. The move function moves the camera and game objects, and draw uses GL to render the object geometry. Close closes the window. X input uses X11 to receive keyboard and mouse input. X next event checks if there's an event in the queue. Here are the mouse variables. This block is key press. This block is for key release. X warp pointer is used to keep the mouse pointer at the center of the screen. I already described the camera orientation and movement. GL clear clears the screen. This GL depth mask gets disabled and re-enabled, and that causes this skybox to be drawn behind the rest of the objects. This block is static objects, and this block is dynamic objects. These state functions signal to GL to use these array types. The pointer functions specify the actual list to be used. For skybox, I want to display a cube map. I want to use an image stored in this array, and GL assumes that the rest of the images follow. New matrices can be added to specify different transformations for different objects. Load identity loads the default matrix. GLU perspective sets up a camera with a viewing angle of 45 degrees and this aspect ratio. GLU look at puts the camera at the center of the screen where it stays. The next three parameters define the direction that the camera is looking. That's the camera's W vector. The next three parameters define the up direction for the camera, and that's the camera's V vector. And here I'm passing 24 quads to GL, and those quads are defined by these arrays. The static object list is almost the same, except it checks what type of shader the object has. It also moves the objects based on the opposite direction of the camera's location. So the objects are moving around the camera, and the camera stays in the center of the scene. I'm using triangles for all static and dynamic objects. The dynamic object block is almost the same as the static object block, except I'm adding these dynamic transformations. And then I refresh the screen. Window.c++ loads the window. Here I declare some global variables that are needed for main, and these are all to do with opening a window, and that involves things like communicating with the device display and creating a screen buffered and drawn. I'm not exactly sure what all of these functions do, but for the most part they're returning information about hardware, or sometimes they're setting options. These masks are needed for the window to receive keyboard and mouse input. Here are some game options. These GLX functions allow GL to communicate with X11. The object.h header defines the camera and object classes. Math.c++ is a math library, and the functions in this file are functions that work for vectors of any dimension, so vectors that are 2D, 3D, even 4D or 5D. The graphics.cpp has more math functions, but they're functions that work for a specific dimension, usually 3D functions and some 2D. Here's the skybox geometry in image.c++. Image load is an example I found on the internet, which I'm grateful for because I don't like processing raw data and allocating memory in this kind of low-level type code. I modified it a little bit because it didn't work at first, but it was still a lot easier than writing it from scratch. The graphics header has vector classes. A lot of these definitions aren't being used, but the object header uses a few of these. And I need to make some overloads like plus equals and times equals. And there are some overloads in graphics.cpp that don't work like they should, but for the most part it is working. So this is the header file that has structures and classes, and the CPP file has functions. And I don't think that hardly any of these functions are being used by the program, but more will be in time. For example, there are functions for finding intersections between polygons, which might be needed to find object collisions. Even though GL detects and resolves intersections graphically, I'm not sure if there's a way for GL to report on that collision back to the main program. And if that's true, you'd have to write collision detection code, which I might actually do in the next little while. Raycast is another thing that GL can find in less than the blink of an eye, and to set up raycasting using the processor instead of the graphics card is a lot less efficient. But I'm not sure how GL might report a raycast back to the main program. To a large extent, GL is kind of like a black hole where data goes in and never comes out, except in the context of what appears on the screen. And if that's true for raycasting, then I'll have to use some of these functions to get a ray intersection. And that's the end of the video. There's a lot of work left to go, but it's enough to get something that could start to resemble a game. So I'll keep updating this video and re-uploading it, but I'm also going to start to put some scenes together and make some videos on how to program some of the game elements, like walk cycles for characters and pathfinding and things like that. So thanks for watching.